Hello, welcome to this section 2A. We are going to get into the definition of a process, the most important piece of a entity that OS manages. And then we'll see what are CPU bursts and IO burst and what is a process context. Then let me explain the most important critical area of OS which is not understood very well, the context switch between two processes. Now let us understand what is a sequential program. All programs are sequential in that they execute a sequence of instructions in a predefined order. Now, one thing we need to understand here is, suppose if I say I am writing some code in the C program language. Maybe I will say that I equal to 10, then I will say j equal to I plus 10, then maybe I will say that function I comma j. And then we'll say that okay, it is returning something. Let me write it into some variable k. Then I'll say k plus plus. These are the set of instruction. Now you may wonder that this is a sequential instruction, right? This is a set of higher level language instruction. But this assignment, what I am doing here, does it really execute without branching off to some other location? No. When I say function, we are calling a function which is maybe in some part of the memory which is defined here, and then we have set of instructions there, and then we return from there in our C language. Now in when you convert this particular C program into assembly programs, there will be set of assembly instructions which could be move I comma move R0 comma R1 or whatever, based on the processor. We have different set of assembly instruction. Now similar to the function call, there is a branch to label, or it could be some other assembly instruction which will, or maybe we'll call it as call function, which is normally some processors follow, is in assembly. Also there is a function call. Either you branch to some location which is equivalent to going to some other part of assembly instruction and executing it, and then we say return from there, it comes back to this. There are different instructions called BXLR in ARM, where you will branch exchange. Link register is used for storing the return address after the call, whatever the function call, where it is supposed to come. The next assembly instruction address will be stored in the link register, and it comes back. So effectively, a sequential program, though it's sequential in nature, it also goes into some other location and comes back and executes its the instructions which are below. So it happens in C language, and the similar thing is happening in the assembly language also. But this is a predefined order. Now going back to this and coming back is predefined order. Okay. I hope you understand what exactly happens when you are executing. Even a for loop is a predefined order. Okay. But it depends on the value of the variable that you are looking for. I less than 10. That means it is going to be in the for loop for 0 to 9. 10 iterations, and then it will come out of it. But that is also predefined in the sense that based on the value of I, when it reaches 10, it's supposed to go to a particular instruction. So let us let us look at a particular assembly instruction where you are interested in doing x plus plus in higher level language. Now if you need to do x plus plus, what happens? It's in the memory. The variable x is allocated some space, and then it has some value 10. Now it's in main memory, or that for our application. Now CPU is what is executing this. It is supposed to perform this x plus plus operation. Now when you do this x plus plus, it is converted into some set of assembly instruction. Maybe I would say this is the instruction which has been generated with the compiler. Now what does this do? If you want to increment any variable inside the memory, some processes allow you to change it directly at the memory location level, but the most popular kinds of processes, which is called reduced instruction set computing, does not allow any arithmetic operations or logical operations performed on a variable which is in the memory. Now anything that needs to be done has to be brought into the CPU. So now we want to increment it. That's an arithmetic operation, adding existing value to and then adding a 1 to it. Now that cannot be done directly by keeping it in the memory. So it needs to be loaded into a register. One of the registers within the CPU, which is here. That variable comes into the register and then add instruction is done. Now here, if you assume that this processor, which is not specific to any processor, it just adds 1 to it. Okay, the value of whatever is the value of r1 is which is there in memory is brought into r1, which gets incremented to 11. Now this should be written back, otherwise the memory will be having 10, but you might have incremented that value here, it would have become 11. Unless it goes back to the memory, the variable is not updated. So store instruction takes care of putting it back into it. So a simple instruction like X++ in higher level language is actually a 3 assembly instructions as far as the CPU is concerned. Now how does it execute? A program counter, which is a part of the CPU in a ARM, you may be aware that PC is nothing but R15, which is already initialized with an address with where the instructions are stored in the code memory. So if I say this is a part of code memory, the load instruction or add instruction equivalent of that in binary form is stored in the memory. So when the CPU is executing this instruction, then it accesses the instruction from the memory and does the load operation. In that case, it goes into the location where R1, where whatever may be the address of X, is loads that content of that address into the register. So understand this, a PC is a program counter which is taking the CPU onto the instructions which are supposed to be executed by the CPU, and then based on the value what is loaded into PC, that particular instruction is fetched from the memory and then the CPU executes it as per the instruction what it has read. So for a instruction, for a higher level instruction like X++, these are the instructions generated by the compiler and stored in a particular location in the memory, and that address of that code is loaded into PC of the CPU when it is executing your program. So it's a sequential execution of instruction, and PC is incremented after these instructions are executed. So if the instruction is occupying 4 bytes, then it will be incremented by 4. If the instructions are just 2 bytes wide, then it will be incremented by 2 based on whether it's a thumb mode or an ARM instruction in the ARM processor. So this is what happens, and the sequential execution is happening. Now what you do, you group all the related operations in a procedure, and then a sequential program is a single flow of instruction. So this is what is called a sequential program or a thread of execution. So understand that this is a thread of execution, single thread. There may be multiple programs with multiple threads executing. Now sequential program with the IO wait. Now suppose imagine we have a device which is a serial device which is connected to the external entity, maybe another board or hardware, where the characters are coming on the serial port and it is received by the serial hardware, a device which is there in the motherboard of your system. Now a CPU, what does it do? It needs to be informed that a character has been received. Now how is it happening? CPU will not know what is happening at the other side of the device, so it keeps polling the device. So it may be this serial device, whatever I'm saying is a small hardware module which has a specific address in the CPU's address space, and it could be memory or IO, but I am assuming a memory mapped IO wherein this address of this serial device, where different control registers are there within them, also have some addresses. So CPU puts that address, tries to read that particular value. Now let me call that a serial flag, which is nothing but a particular flag indicated by the serial port to say that a character has been received. So it is loaded into R7 and it compares with 0. If it is equal to 0, it goes back. That means this serial device will set this flag to 1 if a character is received. Now what happens when the CPU is trying to wait for a character from a device, or it could be from a keyboard? This particular set of instructions are executed in a continuous sequence until a character is received. So it's going to be forever if you don't send any character on the serial port, or if you don't press any keyboard or a key on the keyboard. Now what happens if it is waiting forever? The CPU is executing only this job of waiting for an IO, which is a IO wait. Now as I explained it, this instruction sequence, what is happening, I am saying this. So with a single CPU, imagine if this program is running, there is no useful job done. So CPU is continuously polling and looking for a character to be received. So this is called IO wait. Now what are we doing here? We are wasting CPU cycles. In the sense, CPU is executing at a very high rate, but still the characters are coming at a low rate, and it is waiting for a IO character to be received on the serial port. So the CPU is busy doing something which is of no use, and we are not making any progress. Now, what can we do in case a OS is running? We know that it is waiting for an IO. We could arrange it in such a way that it is not continuously pulling. We can provide an interrupt whenever something happens on the serial device. Let it interrupt the CPU. Till then, CPU can be freed up of waiting for it. It's equivalent to continuously, suppose your friend is going to come and he says that, okay, he or she says that I am going to come at 4 o'clock. What you start doing? You from 3:50 onwards, you start looking at the door or keep opening the window and see whether the car or the vehicle has come, and then you go in, and then you again come and see whether he has come. Instead of that, if you just say that you, when you come in, please press the calling bell, I will come and open the door. So you can do your job internally, whatever you want, without waiting for the person, continuously checking whether he has come or not. So interrupt is a mechanism where the CPU is notified of some event happening. So CPU can go ahead and do some useful job during that time. So what we call a CPU burst here is useful instructions being executed. Suppose you are doing a arithmetic operation, a add operation or mul operation within the CPU, you are keep modifying some contents in the memory and continuously the CPU is executing it. This is called a CPU bus. It is continuously performing some job, useful job. Whereas if you are waiting for some event, it's an IO wait. So wherever IO wait is there, you need to make sure that the CPU is not continuously polling it. It's called polling. Polling means continuously checking whether the something has happened or not. Instead of that, you make it interrupt based. That means when the event happens, the CPU will be informed. Okay, as a asynchronous event coming from the external world to say the CPU, hey, whatever you are doing now, please stop it. I have an event which is completion of something. Then the OS takes control of it and then checks what is the event, whether the particular process needs to be woken up. Then it will take care of doing those things. So what is the benefit of doing this kind of thing is that the CPU is not continuously polling or waiting for some event to happen, and it can be freed up to perform other useful job which is within the CPU it can be executed. So any other process which may have only jobs that needs to be done within the CPU can be brought into the CPU and it can be run. So this is what I call it as CPU bus and IO bus. Any process or any program that you write normally have a set of CPU bus, and then once in a while you will be waiting for some event to happen. It need not be waiting for a character to come from a serial port or a keyboard. It could be that you are updating some data and then you are manipulating some data and then you are storing it in a file. Then that's a IO wait, because storing into a file and then getting back a result saying that okay, the storing has happened or a database. You are writing into a database. Doesn't matter what you do, or you are sending it on a serial port, or you are updating it on the screen, whatever it may be. These are all anything to do with the devices around you or a file system or on the network. It's an IO wait. So whenever these things happen, the job is handed off to some other device to complete it, and then it will be informed that you please send back the information whether that job given to you has been done or not. Then CPU will be notified, and then the OS can wake up the process which has started the IO access, and then it can continue further down on that. So till then what happens? The CPU is used by some other process. Who takes care of that? OS takes care of it by giving the CPU to some other process. So this is what is called scheduling of a program. Even though it's sequential in nature, most of the programs are going to be waiting for some data to come from or to write some data into some file or a IO port. So it has to have some waiting time. During that time, what we can do is we can make use of the CPU to do some useful job. So CPU burst is when the process is being executed in the CPU, and IO burst is when the CPU is waiting for an IO to happen. Okay, because if you are written a program in the sequence, you say f open, that means you are opening a file. Until this file opening is happening, the program cannot go further, because that event has to happen and the file has to be opened and the content needs to be brought into the main memory before your program can go to the next instruction. till then it's going to be an IO wait. So, or scanf. If you are doing no a scanf, that means you are waiting for some data to be entered by the user. In that case also, it has to wait for the user to enter the characters. Now you cannot expect or you cannot anticipate how long the user would take to key in the data. So that's a long wait. It could be a long wait or it could be an immediate thing. But still, from the CPU perspective or from the OS perspective, anything to do with the IO is slow. So what happens? How do you make use of the time? Now imagine I have two sequential processes or sequential program, the thread of execution. There is some CPU burst is happening. Now when this IO burst is happening, what am I going to do? I'm going to push this CPU, this process out of the CPU, and I'm going to bring some other process which has got a CPU burst. So I am using the CPU. If you look at the CPU from the perspective of CPU, during this time, if you draw the timeline, during this time, I call it as a P1. I call this process as, sorry, I'll write it here. I am, during this time, P1 is executing. Here, this is the CPU bus, so P2 is executing, and then P2 goes into IO bus. That time, this guy is ready. So, the next set, I will expect P1 to come into the CPU and execute it. Now, what is the advantage? CPU is always busy. Either it is executing P1 or P2. And one more thing you notice here, we are not wasting the time of CPU for IO to complete, and both the processes are progressing now. Actually, we are going ahead with P1 and P2, both are doing their job, and whenever they are waiting, they are taken out, and then some other process is running on the CPU. So is this an effective way of utilizing the CPU time and getting maximum done out of the hardware you have? So I am calling it as these are the sequences of operation, and this is what is happening. On the CPU, this is the sequence of operation that is being performed. So you can see that alternating between CPU and IO bus. I hope this is clear to you what I mean by CPU bus and IO bus. You can read this content and understand it more. Now let us go into a process. Now a concept of process is fundamental to the structure of operating system. The most important task of any OS is process management. Now what is a process? It's a unit of executing software that is managed independently by the OS. That means one program could be called as a process. That means all the data, code and stack of a process, which is called a resident set, is brought into the main memory, and this process is allowed to run on the CPU. And if it is doing an IO wait, this whole image is kept as it is. It could be moved out, but most of the time it may be in the main memory, and then the focus of the CPU goes into some other part of resident set of other process. So imagine these are all the one single main memory, but P1 process is having its own resident set here, P2's resident set is here, CPU is running. When it is running here, it is looking into these memory locations. When the context is changed, the CPU registers are modified, and the stack pointer is pointing at the stack of this, and the program counter is pointing at the code of another process. Now the context is changed. It's like a battery torchlight. You focus on some part of the house, and then you switch over to another part of the house. You are not focusing on that area. Now the focus is on some other part of the area. So similarly, the CPU is changing the focus of different parts of the memory where different processes are residing, and it knows based on the location of the address what is there in PC program counter, it points to a different address. If you change the program counter, the full context changes. If you change the stack pointer register in the CPU, the stack what it is going to be accessing will also be changing. So by simply changing the addresses of those registers, we are changing the focus of the CPU from one process to the other process. So this is how the context of the CPU comes into play. When you have these registers which are loaded with some values specific to a particular process, when you do a context switch, these registers are modified. Before modifying it, we save it so that when you come back, your context is saved. Okay, it is like a switching the torchlight from one location to the other location. So when you come back, you see what was there lost, and from there you start seeing what is happening there. So similarly, the changes are happening. Now imagine one thing: when the CPU is not focusing on some particular process, that process is on a freeze mode. Okay, don't think that it is progressing unless the focus is there. The CPU's focus is there on the process cannot make progress. When the focus changes, the process is frozen. In the sense, the context star is saved and it is left in the same state as it was. And then the CPU goes into some other location, does some job, and then when it comes back, it starts off from the place where it left off. So this understanding, if it is clear to you, I think you have a better idea of what is a context switch, what is a process, why we are doing saving the context of a CPU's registers. Okay. So what is a definition? A process can be defined as a program in execution or an instance of a program running on a computer, the entity that can be assigned to and executed on a processor. When I say the focus of the CPU is on a particular process, all the addresses, all the register contents are related to this process. And if a stack is used by this process, the stack pointer in case of ARM, it is R13, which is pointing at the current stack of this particular process. And when the context changes, this process is no more active. It is there in the main memory, but nobody is executing it because we are assuming that only one CPU is there and it is frozen. It is on a still, no, it's like a frozen image of the process, and you start focusing on some other process. So unit of activity characterized is a process definition is unit of activity characterized by a single sequential thread of execution. A current state, what I mean by current state is the context, the state of all the registered contents and the associated set of resources. Now when I say resources, the content of the memory. Remember, process is not only what is there on the CPU. It's a current state. It's like a one snapshot of your event. But actually what is there is in the memory. Whatever is the data, what is modified, wherever the stack is currently, what are the local variables are there, they are the current execution information which is there in the main memory. Current state is what are we doing at the moment when this CPU is stopped, and then you save the content of the processor CPU, then you can switch over to some other process and start from where you left off. And then when you come back, you restore the register content. You are now started seeing the process from the place where you left off. And when the CPU is executing it, it makes some progress, like what I showed you on CPU burst and IO burst. This understanding is very, very important, and you have I think I have tried to explain to the maximum extent possible. Now let me explain with the context now. This is the CPU and we have a PC which is pointing at the code area of the one process. Let me call this as a process P1 or A, or I am calling it as a B here, and this is process A. Now CPU is changing its focus. Now you need to maintain or store somewhere the context when you are switching over from one process to the other process. Where is it stored? It is stored in the process PCB, which is called process control block, a part of the OS data structure. And when a process context is changed, the all the contents of these CPU registers are stored in the PCB, because every process has its own PCB entry and its own PID, process ID, and they are having the different locations in the OS area where this context is saved. So let us just go further. OS allocates some memory for resident sets of each process. So resident set means the data and code and stack and other things are not shown here, but please understand that they are also part of the resident set. OS maintains an index into the start of the memory block. So normally it need not be start of the memory block. It could be entire memory, could be distributed. It need not be. Please remember that advanced operating systems do not keep all of them together in the main memory. It can be distributed across different part of the main memory, but OS knows where they are, even though they are at a different locations. Okay. So each process is also given a unique ID. It's called process ID. Assume that CPU has two registers. We are assuming that it has a base register and limit register. Why? Because we want to make sure that the when this process is running, it is only executing or accessing only its own memory. So this is a simpler implementation of it, but in generic OS, it may not be implemented this way. So now I have already explained you the context. Now let us understand them. What's the context? Imagine the OS needs to remove a process from the CPU. What needs to be stored by the OS? The status information of the process or a context which is executing on the CPU. OS needs to store the needed information of a process before removing it, because if you remove it, all the content is lost, because some other process will come. Even when the OS is running, the context is lost. So even before the OS runs, the context of the existing current running process is saved. Okay, that's how OS is built. Because remember, even if OS to run on the CPU, it needs to take control of all the CPU registers. That means its own code will be running, PC will be pointing its own OS area, and then its own data. Please remember, OS also has its own data, because it is maintaining about each process in the system. It maintains a PCB, it maintains PI areas for all the processors. So it has got much more things to do than a simple user process running on the system. So one important thing to take care here is the correctness of the process. When you are removing a process, you have to make sure that when it comes back onto the CPU, it starts from where it left off. If you remove some instruction in between, if you forget to execute some instruction, what happens? User wanted to do something, and the OS, because it is doing a context switch, it has failed to execute the instruction. That means it has not done the job that OS, the user wanted it to do. So it has to be guaranteed. OS needs to make sure that the user processes are run as per the user's intent based on the program execution sequence. Okay, so this is the context process. Context includes the contents of the registers, and register values are preserved in the OS area, and then it is brought back when it is due for running on the CPU. So that's why most of the time this context switch, or always context switch, is performed in the assembly language. I think I have mentioned in the previous lecture also. I hope this lecture was useful for you to understand what is a CPU bus, what is an IO bus, and why we need to switch between these two, because CPU wants to be utilized fully, and what is the context and what is being saved. I think if you are clear about it, you are ready to take on some more deeper dive into operating system, which is an interesting area of computer science. Bye bye, see you in the next lecture.